Hi guys, welcome to the video series in traffic assignment. Why I'm saying video series is because if I do the entire module in one video, it's taking a whole lot of time trying to render it and upload it and all that. So it's not a productive use of my time or your time to watch the one full video at a stretch. So instead, what I decided to do is divide into small chunks, and that will help me reduce time in uploading, rendering, etc., etc. So I really don't know at this point how many videos will be, how many short videos on traffic assignment will be. This is module six of course, traffic assignment, step 4 of your 4-step planning process. So number of videos, I would say at least 10, maybe more. Okay, let's get going. So this is the first video in the series, which is, let me put number 1 here, intro to traffic assignment. Here we are just going to talk about what is that we are, why we got here, what is that we are going to do in traffic assignment. So by now you probably are sick of this particular drawing here, which I keep forcing onto you at the beginning of every module, right? So we talked about socioeconomic data, travel surveys, etc., etc., and we talked about networks as a part of module 2, and then we went to module 3 with trip generation, module 4 trip distribution, module 5 mode choice, and now we have module 5. I'm sorry, module 6. Can't even count. Module 6, what happened here? We skipped a few steps, or looks like we skipped a few steps. Anyway, module 3, 4, 5, and 6. So maybe I'll better explain it in the next slide here. Essentially, the output from mode split is not going to be a direct input to traffic assignment. There are a few steps in the middle that needed to be taken care of. They're called sub-steps or side steps. We will get back to them in module 7. Okay, so bear with me. So basically, what we have right now is in this module, we're going to talk about traffic assignment. So what are we going to learn here today? We will learn how to find shortest paths. It's not like we don't know how to do it in our minds, but we have to have a methodical way of doing finding shortest paths. It's also known as algorithm. Algorithm. We will find out a most popular algorithm which does that. It's essentially implemented in a variety of pathfinding algorithm, including your Google Maps, where you ask for directions. I'm pretty sure something similar is going on in there. I don't know. They're not going to tell you what exact algorithm they're using to give you the shortest path when you ask for directions. Anyway, the next one we're going to learn is something, I mean, you should know what are different assignment techniques and explain the concepts behind these assignment techniques. And there is something called capacity constraint or capacity restraint algorithm. In other words, when traffic increases on the road, speed decreases, right? So when you take that into account, that is called capacity restraint. And the fundamental building blocks of that are speed flow relationship, and that is essentially a BPR formula. Well, BPR formula is a very popular speed flow relationship which is used in traffic assignment. You're going to learn a little bit about that. So the next one is we are going to solve some problems with each of the assignment technique we are going to look at. And not only that, we have to interpret and explain the meaning of volumes from different assignment techniques. And then you should be able to compare which is better and which is not. So one thing I want to point out here, so the purpose of making this video is to have some sort of a reference for you. The NCHRP 365, which is your textbook, is grossly inadequate when it comes to traffic assignment. Unfortunately, I wish I could have given you a different textbook for you, but we cannot have too many textbooks. So what I did is I compiled a whole bunch of these, a lot of this material into this presentation, and doing my best to communicate with you all the procedures, philosophical underpinnings, as well as problems through these videos. So this presentation and the videos are very important, so they should be your reference. And another thing is, in your undergraduate textbook, Chapter 8 of Intro to Transportation Engineering by Mannering and Washburn, this, at least in one of my previous offerings, I did not have enough time to cover it completely. So we will revisit some parts of that. So reading chapter 8, especially what's related to traffic assignment in chapter 8, would be useful. And one other thing I want to say, of course, you can see how important it is because I put it in red. This topic is very intense. It has a theoretically, it's very complex theoretically as well as practically. Why I mean by practically complex is that, so this is the part where I said quite a bit of computer science comes into this discipline. And it's not that you should understand all the computer science aspects of it. There are advanced courses in traffic assignment where that will lead you there, but you should have some basic knowledge about this. If you know the fundamental principles behind it, and if you are able to solve small problems using calculators and spreadsheets, you will at least understand or have an appreciation for the complexity or the computational complexity of this problem called traffic assignment. Let's recall some of the past. So what did we have at the end of trip generation? We have a trip table. For each zone, you have number of P's, number of A's, and if you had n zones, each zone is like that. And in the end, both P's and A's are, what are they? They are balanced, meaning sigma P is equal to sigma A's. And this is your output of trip generation. Because we have a sequential process, the output of trip generation, which is step 3, is going to be input of step, wait a minute, not step 3, this is module 3. So this is step 1. Okay, I know I misspoke. Step 1, output of step 1 is going to be input of step 2, which is trip distribution. This is step 2. So this is the output of trip generation comes to this process called trip distribution process. So remember the gravity model, etc., etc. And then if your matrix is actually it's a, so it's not a square matrix. This is 3 columns in this matrix, the input matrix to TD process. When you put it through trip distribution process, you have a square matrix. This is a square matrix, meaning from n zones to n zones is a square. N times n, this is n times n, this is n times 3. So that's the difference. Now, one of the most important things you have to keep remembering is here we have person trips as well as here person trips. We haven't gone to the vehicle trips yet. Now that trip purpose specific trip distribution output will now become input to mode split, and you run through the mode split process for each zone pairs where there are alternatives clearly specified. Remember I said what I mean by each zone pair. This is not a universal mode split across all zone pairs. You will not put transit trips in a zone where there is no transit service or into a zone where there is no transit service. That is why where they're coming from, where they're going, what modes are available is also important. So when you process this through, you will have two types of outputs that come out. One is a transit trips table. Usually what they do is transit trips they combine for all purposes because they're going to be person trips. So if you're a person trip, two people, they go by bus, all two people they get on by bus. So that is how it is. Whereas on highway trips, if you have four people, maybe they use one car, maybe they use two cars. So that's why here you don't still combine them. You maintain at this point. You still maintain the purpose. So up to this point, we learned this is your step 3, or in our case, we use that as a module 5, right? Up to this point, you are maintaining the purpose, trip purpose. Now, this is a step we will revisit in module 7, little bit, not in detail. Module 7 we will revisit. Now, this part is the output of mode split, and you funnel it through the process called time of day and directional factoring. I'll just give you a gist of it. We won't cover totally, and that directly goes as an input to transit trip table by time period. Now, what do I mean by time period? Earlier, typical trip generation, distribution, and mode split process happens on a 24-hour trip table. And then they take that and split it into morning, afternoon, peak periods, and 24-hour. And sometimes they do an off-peak period too. So it's as we go a little further, you will have an appreciation for that. So anyway, so of course it's important because if you have metro service, there is a peak period service, and then there is an off-peak period service, and then there is a weekend service. So the frequency of transit changes by time period. So therefore, you have to have a different assignment for different time period. Same thing with highway assignment too. So highway assignment vehicle occupancy is an important thing. If you have, you are maintaining, remember, at this point here, you are maintaining the identity of trip purpose. Home-based work trips, for example, will have lower vehicle occupancy than, say, home-based social recreational trips where more family members might join. Okay, that's the reason why you maintain this separate identity, and you find out how many trips during a particular day, particular time period of the day, and then purpose specific vehicle occupancy, bingo, you get vehicle trips. This is where we got V trips means vehicle trips. So this guy here is a consolidated vehicle trip matrix for all purposes. It's consolidated for all purposes. And he is the one that is going to your traffic assignment procedure. So quickly, what I mean by time of day? Let me give you a gist of it. What a time of day is. I said it is a 24-hour trip table, right? Trip table. So imagine what is the percentage of trips you make in the morning versus afternoon. So just like in your household, the entire region has certain split in a daytime, in any given day. So maybe about 10% in AM peak. You have seen this in ITE trip generation manual, right? So 10% of the trips coming in AM peak, something like that. So you sort of, I mean, I'm telling you very loosely at this point. Sort of like take 10% of that, and then apply direction, whichever direction you go. Home-based work, which direction they go from home to work. So probably 90% of these 10% are going from home to work at the morning peak period. So you will apply such kind of an adjustment. So very unlikely at 7 a.m. you will have shopping trips, especially mall shopping. Most malls are not open. So you get the picture. So directional factoring and time of day factoring. We'll revisit in module 7. Now, earlier I showed you a square matrix of vehicle trips, square matrix from n zones to n zones. Just give you a pictorial representation of it. This is Washington, D.C. metro area. So R stands for a residential zone, and W stands for where there are work trips. S stands for shopping. So Tyson's here has residential, shopping, and work. If you, I mean, same with Arlington as well, Washington. I just took it as a representative set of zones here. So here we are in Gainesville. These guys go all the way to DC, and maybe somebody who's residing here go to University of Maryland, and the person who's residing here is coming to GMU. Somebody here to GMU. He's going to work there. So I'm just pictorially representing this matrix. So let's give another, okay, this one here. So all these, you can see this arrow as a desired line. If you have the thickness, if you represent it by a thickness as representing certain number of trips, these are called desire lines. Desire lines. Anyway, that's one of the ways you visualize your trip matrix data, or the vehicle trip matrix data, and then identify corridors. Corridor is east-west direction is a corridor. So in this particular case, let's say 66, Route 50, and what else is Little River Turnpike. They're all together could be a corridor, right? So something like that. I'm actually digressing here. Now you get the picture. That is your trip matrix, and that is put into as an input to time period specific highway network. What do I mean by that? Time period specific. Imagine morning peak period. Your HOV lane on 66 is only eastbound. Westbound, it's open for all. So if you have HOV vehicles, you don't, if you have only single occupancy vehicles, you don't put them on HOV lanes. In other words, single occupancy vehicle lanes are fewer on 66 eastbound in the morning. So your network has to be very specifically coded for that kind of a nuances. So that type of network is prepared, and then you have the trip table, the network. They go into this. Well, it's not actually a black box. It's fairly. I know what is in there, so I don't feel it's a black box, but it is. This is very cumbersome. Some procedure. Sorry for the handwriting. It's looks like gibberish. Anyway, then comes loaded network. 66 between exit 62 and exit 60 and 62 eastbound. X number of vehicles. The program tells you under the scenario you are studying, and that's the output. That's your main goal of traffic assignment. So let me give you a quick terminology recap. It's highway assignment. We call it trip assignment, traffic assignment, traffic assignments, etc., etc. And then transit assignment is a whole different animal. All or nothing assignment is a technique which you are going to learn. Technique. Equilibrium assignment is part of your, actually, this is in your chapter 8 of Mannering and Killaresky. I'm sorry, not Killaresky, that author is no longer on that book. So Mannering and Washburn. We will have the speed flow, travel time flow relationships, and the brief BPR function. So we will learn about path finding, impedance, path loading, level of service. You know already, capacity restraints, key screen lines, and cut lines. We can introduce them here or in module 8. So it's better talked in module 8. So what we want to know is which route, if you have traffic from A to B, which route will they take? They go this way or this way? Or this way? That's the question. So what if everybody takes the same route? That would be nothing but all or nothing. Now, some people might take this, and some people might prefer that, and some here. So that depends on the traffic, meaning volumes. That is when the capacity restraint comes into picture. So essentially, that's where we are headed. So the methods we are going to learn are all or nothing, stochastic method, capacity restraint assignment. Within that, you have incremental method, iterative method, and equilibrium, user equilibrium, and system optimal. So again, we are not going to touch upon in this course transit assignment, and which is totally different. Of course, for want of time. Yeah, that's the end of part 1 of transit traffic assignment. End of part 1. Sorry for the poor production value. So I'll see you in part 2.